Okay, good morning everyone. So I got feedback that you have some ambiguity about the project. So I'm not sure what actually you are looking for and what actually you have some ambiguity, but here I want to clarify you that you give me the data set and to research questions. But I ask you by the end of March, you will have to submit your data analysis plan. Is it clear to everyone what the data analysis plan? And including the justification of the proposed analysis. Why you are using this data analysis plan? Why do you think that based on your research question this plan is good or not? So this is what I am looking for at the end of this month. You may submit a draft analysis for the feedbacks. It's up to you. But it's not required. But you need to tell me, because when you give me the data set, we had the meeting, I told you that, okay, this is the data, it is approved. Okay, now you can start working on it. But which method you have to use, you have to decide by yourself and give me the plan why you are using this method. Why do you think that this method is appropriate for my data plan, for the analysis? Okay, because we learned so far many different methods like ANOVA, ENCOVA, multiple regressions, and very soon we'll learn the logistic regression. So you need to tell me why you are using, what is the justification, and if you think that, okay, we are quite sure that this is a good method or good plan, then you can do the draft data analysis just for the feedbacks. So this is I am expecting from you by the end of this month. Any questions? Or any confusions about the project?
Dr. Chowdhury, I have a question real quick. How long do you want this the data analysis plan?
So it can be 1 page, it can be 2 pages. It depends on how you are writing or how elaborately you are explaining the stuff. Okay, you can say, okay, this is the plan. Okay, this is the assumptions for the models that I am going to use, and why you are using this one. Why do you think that this method? Because we know in every chapters when we talked about this, we said that, okay, in this chapter we are learning this because this is good. Why we cannot apply the other one? So you need to also explain this part just in a 1 page. Maximum, if you can elaborate more than 2 pages. 1 page is also okay for me. I need to know why you are using this one, what's the questions, whether you can answer these questions from this data analysis plan, and so on. And also you need to write your justification with the model assumption, because in every plan we have some assumptions that we assume this and that, so you need to just write it down. Any other questions? So if you don't have any questions, I am assuming that you don't have any ambiguity about the project now. Okay. Now, we already finished 3 homework, so you can see our next homework will be due in April 2, and the last one will be in April 23rd. And then we'll have the final exam, which will be the take-home one, and I'll give you the dates for the take-home final exams later on. And in the meantime, you will have the midterm too. Any other questions? Feel free to ask me, let me know that you have concern about this. If you don't ask me, I'll assume that everything is going good with you. Okay. Will the midterm 2 be the same format as midterm 1? Yes. It will be the same format. I will give you like 24 hours with the questions and the chapters. I will let you know when the time comes that which chapters we will cover in the midterm 2. So far in midterm 1 we covered until ANOVA, one-way analysis, that means the one-way ANOVA. So obviously the midterm 2 will be from 2-way ANOVA, then ANCOVA, and then we'll see how far we can go until midterm 2. But the format will be same. You will get some practice questions as well. So you will do some practice problems. We will do some review session for the midterm as well. And the timing is same, 24 hours to complete the midterm. Any other questions? Okay. Okay, so if you don't have any questions, we can start. And also another thing, that based on the feedback, that let's say if you ask me a questions in class, and if you see that I am giving you the wrong answer, that means not the wrong answer. Let's say if you say that, okay, you asked me this one and I said, okay, this is from this part. So you can just stop me, okay, this one is from, I am asking this one. So sometimes as a human being, it can be anything happens, like we can do something that different from what you asked me. So you can just stop me that, okay, professor, I ask you this one, so can you clarify this one? The one thing. The other thing is, if I am going fast and you can't follow me, you need to let me know. Okay, if you don't stop me, if you don't ask me, I don't know that whether you cannot follow me, because first of all, most of you are not in class. Suppose today there is none in the class. So all of you are online, so you need to stop me, because I can't see you. I can't even see how you are doing. If you are in the class, I can see your face, I can ask you several times, but since you are online, it's better to stop me and let me know, and I can stop myself. I can go over these materials one more time. That's not a problem. It's better to let me know. If you don't let me know, I don't know whether you are okay with this or not. Okay, so let's go back to our chapter 13. So if you remember, in the last class we finished chapter 10, the ANCOVA. So and then we are going to the 11 and 12 we are not covering in this course. So we are going to the chapter 13. So I uploaded the solutions for the class question for ANCOVA. If you go to the class question solutions, you can see this. Now, what is about the chapter 13? At the very beginning, you told me that how we can recognize whether this is an outlier or not. So here we will learn all these things. So I told you that we will discuss more details about this in the later chapters. So here is the one. So we call it, so far in chapter 1 to 10, we discussed about the models and the data. We didn't discuss anything about the error term. In this chapter, we will talk about more about the error term. So if some of the assumptions are violated, what we have to do, or if we have what is called the non-constant variance, we call it heterogeneity, or if the residuals are large, what is the procedure, how can we do it? So far we have been making the assumption that the error term follows the normal distributions, okay? And also we assume that there is a constant variance. So this is all about the error term, we just assume it, but we didn't check it whether it is normally distributed, whether there is a constant variance or something else. So these assumptions, why do we need this assumption? Because if we don't assume this, we cannot do the F-test and we cannot get the constant variance. So that's why we always assume that error term is normally independently distributed with mean zero and the constant variance. Now there are two ways that our assumptions can be violated about the error term. One, we call it idiosyncratic violations, which arise from outliers or very weird observation. That means the observation that is unusual compared to all other observation in our data. This is one way. Another one, we call it the systematic violations. That means which leads us to doubt about our p-value. That means our p-value becomes large. So we can check this one by using the residual plot. So these are the two things. One, we look at the outliers. The other one, the other type of violation, we look at the residual plots. We have seen earlier a little bit about that if the residual plot is fan shape or the cone shape, we call it that there is a violation of the constant variance assumptions. Or we also look at the normal quantile plot. So this is what we'll learn more details about this. So both of these violations, okay, can affect our assumption of normality and the constant variance. So constant variance, we call it homogeneity, and the normality, we know that we assume that the error term is normally distributed, so which we can look at the normal quantile plot. And the constant variance one, we can look at the residual plot. So this is called the systematic violations. And idiosyncratic violation, we look at the outliers, whether there is a wild observation or unusual observation in our data set. So outlier can occur in many ways. Sometimes when we input the data, that means input the data in the data table, maybe we make an error. So instead of putting this, we mistype something, so we call it this is a typographical errors. Or maybe we switch the variable lengths. Instead of height, we put weight, or weight, we put the height, so that's, we can get some unusual results. Now, if we have outliers, okay, how can I identify this? The simplest way to identify this, we look at the scatter plots and find out whether there is any unusual observation in our data set. If this is unusual, we consider these outliers just by visualization. But we can still look at this whether it's actually an outlier or not, whether it affects our regression lines or it's make an impact on our error term. We call it the sum squares of the errors and so on. Now, after finding out, yes, this is an outlier, now we need to know whether removing these outliers can dramatically change our analysis or not. So this is one of the most important things. Or should we keep the outliers? Now let's look at one example here that we are considering here. So this is what we are looking for. Now outlier can happen in two ways. One, we call it if we have large predictor values. If the value of our predictor is unusual, that means we can say in other words large X values. So this is what we call it the Leverage point. If the X values are large, we call it the Leverage point. If our Y values or response variable is unusual or response variable values are unusual, we call it outlier. Now, when we are detecting this, we need to know, does this observation really make an influence in our regression models? If we remove this one, or if we keep this on, what changes it happens? So that's why I consider a data set, we call it the cycling exercise data. I uploaded in ELC. If you go to the ELC here, So open this data set, download this one, cycling exercise data. So in this data, what we are looking for, would like to know elevation gain has an effect on the burning calories. Okay, so we feed the models based on the calories and the elevation gain. Okay, so we go to the analyze, feed model. Now our response variable is calories burned based on the elevation gain. Just I am considering a simple regression models. We already did one time, but here I am going to show you. So can you follow me how I am doing? Everyone is okay what I did so far? Yes, okay. Now click OK here, run. So now you can see here, we can see there are some unusual observations. For example, this one. If you look at this one, this is a point in the row 2. Okay? So these points are far. Also this one is far from the usual observation. So if you click on this, you can see that these points are highlighted here. Okay? Now, this is the 2 points that I just here pointed out. You can see now we consider these 2 variables, the calories burned based on the elevation gain. Now we'd like to get an idea, is the value of our predictor unusual? That is, do we have a Leverage point? So I uploaded separate additional files in ESC for reading the distinctions between outliers, influential observation and Leverage points. Please read it. What I mean by this one, if you go up at the very beginning, I told you that I will discuss this one. The distinction between outliers, high leverage points and observations. So this one, please read it. And here I am going to discuss about this part. So let's go back to our lecture notes. Now I want to get an idea of one, that means whether we have a high leverage point. So we fit a model using calories as the response and elevation gain as the predictors. Now at the beginning we are looking at the visual inspection, that means just looking at the scatter plot. By visual inspection we can see that these 2 points look unusual. Because they are weird values for the predictor, that would have to be the leverage point. Why we are saying the leverage point? Because they are large X values. X values mean the predictor values. For reference, these values are the row 2 and the row 6 in order of decreasing weirdness. So you can see that when you click on this, so if you let's say, how can you select that in our jump output? You can just make a box here. Okay, if you put your cursor like this and make a box like this, you can see that if you look at data table now, you can see that these 2 points are selected in your data table here. So these are the 2 points, that means these are the 2 rows which have unusual X values, we call it the leverage point. But how large it is, we need to know. So this is what we are going to discuss now. So maybe I can clear the states now. We don't need it now. But this is how you can detect it. Now when we fit these models based on these 2, only one predictors, you can see our R-square is only 17%. Our F value is small. Since we already get the significant effects, but we can see F value is small, and we have P values which is smaller, but we can reject it. But our R-square is not high, only 17%. We can see that we have a significant models. This is what I mean by significant model, means our P value is small. You can see that elevation gain is significant. Parameter estimates is the same as this one, P value. When increasing elevation run by 1 increases the calories burned by 0.6088. Why we are going the 0.6088? Because this is our parameter estimates values. But this is not a big gain. Now we also want to see those 2 points pulling the slope here. If you feed the line here, you can see that these two are pulling the slope towards this point. Okay, when you feed the line, you can see the slopes are little bit in this side because of these 2 points. Now the question is that, can we improve the models? And we can look at our R standard error and our R square. We can see that sum squares of the error here for the ANOVA model, which is high. This is the sum squares of the error, which is high. And also you can look at our R square, which is very low. Now the question is that, can we improve these models? So by visual inspection, we can just see that there are 2 unusual points. But we cannot make a decision that whether this has a large influence on it, or how large it should be to consider is an outlier. So the visual inspection is not just enough to tell that, okay, these are the outliers. So we now look at, we call it the head values, which indicate that a leverage a given point exerts on the models. So to get the head values in R, in JUMP, you can use the following. I already give you the head values here in my data, but I will show you that how you can get these head values, okay? So we call it the head values means the leverage points, how big it is, okay? So how can we get it? I gave full description of this. Then you feed the models, drag calories in the Y column, add elevation gain in the construct model effects, click run, and then click on this small red triangle beside the response calories and choose shape columns and click heads. So if you do this, we already did the other part. Now we are clicking on this red triangle besides this. Now, shape columns. Can you see that one option, shape columns? Now the shape column options, if you go down, you can see there is an option equally heads, and this is called the head values. I already have in our data table, but if I click on this again, you can see that in the JUMP data table it will create another head values, the same values, because we already have this one. But this is how you can get your head values. Okay. So I am deleting this one since we already have this one in our data table. But in the exams, I will not give you these head values. I will say that calculate the head values and look at this. So how to calculate the head values is simple. After fitting the models, you just click on the response calories or whatever your response variable name is, and then choose shape columns and click heads. Now the screenshot of these head values are, I just put the screenshot of this one, okay, here, and you can see that 2 red rows here, the row number 2 and the row number C. So they have, compared to other head values, they have head values that is little bit higher. So most of other head values are fairly low, but the 2 rows that I just told you, that 2 and the 6 have leverage value. These head values, we call it the leverage values. These are 0.37 and this one is 0.12. So these are quite a bit higher than any other value in this list. Now the question is that, what is high actually mean by this? So by definition, the sum of the head values should be equal to the number of predictors or the number of parameters in the model, not the number of predictors, number of parameters in the models. Now when you fit these models, okay, how many parameters do you have? Can anyone tell me? We fit a simple linear regression models. How many parameters do you have? So Jack says 1. Now the parameter means we have the slope and the intercept, because the intercept we consider is also parameter. Keep in mind, the parameter means we are estimating this. So we have one parameter for the predictors and the other one is for the intercept. So we have two parameters in these models. Is that clear? Because when you fit the simple regression models, if you remember, in the simple regression models, y equal to beta 0 plus beta 1 x plus epsilon. So we have two parameters, one is the beta 0, another one beta 1. Okay, now, so since we have two parameters, so we are saying that sum of the leverage point must be equal to the number of parameters. So a sum of hi should be equal to 1. Sorry, should be equal to 2 in our case. So now if all the observations in our data set are equally contributing to the regression, then the contribution for each observation should be equal to the p, that means number of parameters divided by n number of observations. So we can say that they are equal proportion, equally contributing. Now anything larger than this, that means if the head values are close to 1, indicates the single parameter in the model is estimating that observation. That means we consider this as a large head values. But here if we look at this, so what we expect in our case, so p equal to 2, okay? How many observations do we have in this data set? So if you go back here, 36 observations, so 2 divided by 36, so what should be the contribution for each of these? We expect that the contribution for each of these observations should be 0.06. Now we can see that two observations, our head values is much higher than this. One is in the row 2, another one in the row 6. And this is what we mean by here. Now we don't have anything quite so extreme because it's not very close to 1. But we do see that these 2 points getting more than their share on this model. So if our goal for this model to describe our data, we should just describe all the data, not just 1 or 2 points. So here we can see that, okay, based on our head values, these are the two values, they are contributing more, but still they are not very high. Okay, now the question is that is the data unusual? So we looked at this one. So is the value of our predictor unusual? Now we'd like to know whether our response is unusual. So how can we find it out? This one. So we are going here to get the idea of 2. 2 means whether our response is unusual. We turn to our data again. We'll now use the distance to predict the calories. So to know whether we have unusual y observation, we need to ask unusual with respect to what? So we're gonna now feed the models with the distance. And then we look at this, okay? So how can we look at this? So to know whether we have an unusual observation, we always look at the residual values. Now, if we find that the residual is very high, so we can say that this is unusual. Okay, so we look at this one, so y minus y hat. So what is y? Y is our data values or response variable values, and y hat is the predicted values. So how far the data values from the line values? So this tells us how unusual our observed value with respect to our predicted value. If our residual is small, it's not at all unusual. Now, since the residuals can be calculated in different scale of the unit, so we always standardize it. So we call it the standardized deleted residuals. So let's look at this data set here. So this is our data. We look at our residual plot here. So what can we see in the residual plot and whether these values are unusual or not. So do you see any residual values are very far or very high in these data points in the residual plot? We can see here, this is our zero line, you can see. So the values are mostly around the zero line except this one. What is this one? This is the row 2. What is this one? Row 6. They are far. This is what we have already seen in our leverage values. Now we can see that for these two values, our observed values are far from the predicted or the zero line. So that means we have high residual for these two rows, because the points are very far, especially this one is very far, which is row number 2. And this is also row 6, and if you click on this. So now, what can we do? So, if our residual is a big, so the model will fit it very well. If it is a big residual, so the model will fit. If we don't have an easy time identifying, so we can look at the studentized deleted residuals. So what I mean by the studentized deleted residuals and how we can find it out in JUMP, I'll show you. Now the studentized deleted residual is just found by first removing that observation from this data and then refitting the model. The residual for this observation is now compared to the model where the value does not have any influence. And then we can calculate it by using the JUMP. So this is the JUMP formula that we can use to calculate these studentized residuals. How can we use this one? So JUMP will give us our absolute residuals or our studentized residuals, not our studentized deleted residuals. But if you want this, you have to calculate this from. So studentized residuals, you can get it from the JUMP here. So when you fit these models, if you go back here, just the studentized but not the deleted one. Again, save columns, and you can see that this is called the studentized residuals, but not the deleted one. So if you go back to the JUMP data set, you can see there is a column, we call it the studentized residuals. Now the residuals are usually positive and the negative, you know this. It can be the points are above the line or below the line. Now what can we see here? So what we expected, what should be the band? Can anyone tell me? We easily expect that the residuals, if it is inside negative 2 to 2, that's okay. If it is outside the negative 2 to 2, so they are unusual observation. If it is outside negative 3 to 3, that is very unusual. And extremely unusual we call it if it is outside negative 4 to 4. So why we call this one? Because we know that we expect that the error term should be normally distributed. And in the normal distribution, we expect that 95% of the value should be within 2 standard deviations of their values. Now, if we find something outside these 2 standard deviations, we call it this is unusual, because we expect 95% of them should be inside. Now, if we get 3 standard deviations below or above the mean, that is very unusual, because we know that in normal distribution we expect the 99.7% of the observation should be inside 3 standard deviation. So here what we can see in our studentized residuals, not the studentized deleted residuals. I just calculated the studentized residuals from the jump. If you look at the row number 2 here, this row, you can see that this values, the residual values is negative 3.75. That means it is outside of this negative 3 to 3. Do you see any other values that is like this in our data set? So we can see this is just 1 point something, that's fine because it's between negative 2 to 2. We don't see any other values in this studentized deleted studentized residual, that any other value that is below negative 2 or above positive 2, except this one. So this is how we look at this. So now I ask you that, okay, JAM does not give you the studentized deleted residuals, but you need to calculate it by yourself. And how you can calculate it, which is actually the key test for testing whether we have a studentized residual that is significantly different from 0. And where HI is the leverage value, EI is the residuals for the ith observation. Now SSE is the ANOVA for the model, and we can just go and drop this on, and then from the residuals we can calculate this on. And then we look at whether there is an effect on this. Now another important thing, now you can ask me how we can do it. You can just go here. So in this case you need to know the residuals. What you need your residuals. You know what is your sound squares of the error. You need to know your HI values. So how we can get the residual values in JAMP? So if you feed the models here and then save columns, and you can see there is a options, we call it the residuals. So these will give you the residuals, so we call it the EI in this case. So the residual of the calories, we get the studentized, so you don't need this one to calculate the studentized deleted residuals, but you can look at the residual calories, H calories values here, which is called the head values, and then you use this by using this formula column. So you just go and click on the new columns, okay? You give any name, whatever the T values maybe, you put it. Then go to the column properties. On the top you can see there is the formulas. Now you have these formulas. Okay, now you have to put what you are looking for. So based on this formula here, you need to put the square bracket, residual square, n minus PA. So what is our n in this case? We know in our data set we have n is 36, so n is 36. PA, number of parameters in the model. In our case, what is the number of parameters? So we have simple model, so we have 2 parameters, so the PA is 2, n is 36, and then you put everything. So how we can put the square root? First you put the square root like this. Then here, they're going to ask you what is the value, so square root means 2, so you just put 2 here. And then you put your formulas here, the EI square. So EI means our residual values, so our residual is this one. Then you are taking the squares of this one, so you take the square, the power, you put 2 here in the power. So you get this one. Now you highlight this box, and then you need to multiply this by n minus PA minus 1. So n is 36, PA is 2 and 1. So we know that this should be multiplied by (36) 2 minus 1. So please stop me if you are confused that what I did here. So you can see that n, so residual square, okay, n minus PA minus 1. So I just used this one. Now this is our numerator. Now this is what we call it the denominator. So how we can get the denominator? Because you want to divide this whole thing by the another part. So you just use the division sign here, and then you have to put these values, sum of squares of the error. So what is the sum of squares of the error? You go back here and look at your sum of square for the error here, which is 775840, sorry, 775854. So you can put these values here, 7758, and let me go back one more time, 54. Okay. So this is our sum squares of the error. Then what's next? Times 1 minus hi. Okay. Multiplied 1 minus hi. We know that hi means h calories. Okay. Minus, because the next one is the minus ei square, ei means our residual calories, which is ei, square it by putting here power 2. Okay. So now you put all your formulas here. You can see that we put the residual calories. You guys got this part, or everyone is okay how I got this one? Okay. Okay. Now, since you get this one, you click OK here. Click OK here and go back to the data table here, and you can see we have the t values here. So the t values means this one, which is the test statistic for testing whether we have a standardized procedure. So hi is the leverage and this. Now, so this is what I showed you how you can get it. Now of course you have to consider this is really a separate test and this one. So and then we look at, this is called the studentized deleted one. Now we look at whether there is any value that is above 3 or negative 3. We don't see any values in the studentized deleted deciduous or the t values. So here, only one value that is far from 4, even above 4. So none of these values. So here you can see that in all other cases, so for the studentized residuals, studentized deleted residuals, we call it the t values here, we just give the name as t values. We can see that the points here in the studentized deleted residuals for the row number 2, this is very high, above even 4. So we said here that if the points are bigger than 3 or 3, so we can say that the rule of thumb is that large studentized deleted residuals are those that are bigger than plus 3 or the minus 3. Those observations demand extra attention, but any studentized residual that is bigger than 4 or negative 4 to positive 4 really cause an alarm for us. So in our data set here we can see that these observations here makes a studentized residual very high. So this is a problem. So this is how we can say that this is high or not. Okay. Now if you delete these observations and refit the models, and then you can see whether it changes the data a lot or not. So how can you delete this row? For examples, if we just delete these rows, now if we refit the models, we already fit the models using all these observations. Now we are fitting the models with only the observation that is not high studentized deleted residues. So let's go back to the previous one that here we can see that our R square was 29, our error was this. After deleting these observations, our R square is 58, error is lower. So this is what the impact you can see, and if you look at the F values here, F value is much higher, 48%, our P value is also very small. So you can see that impact of the residuals has an impact on, like impact of this what is called the high leverage point or high or outliers. We can see there is a high impact on the sum squares of the errors, R squares, and this is what we can see from this data. So here we refit the models after deleting this observation. Now how can we detect this observation is an outlier? You have seen that how we can check it. You can calculate the residuals. Only thing, the studentized deleted residuals, the JAM does not give you directly, but you can use the formula to calculate this one. Okay, now so the next one is whether we should omit this point that affect the predictions. How do we know that if we exclude an outlier would have a big impact in our model or not? So we can get it by looking at the measure, we call it the Cook's D. So JAMP will compute for us. So a Cook's D indicates that we have very different models when we have the observation that is included and it is not included in the models. So it is an argument that we have high influential observations. So generally the Cook's D, we say that if it is higher than 1 or 2, this is high influential observation. So how can we get the Cook's D? So this is our model that we fit. Now very simple to get the Cook's D. So save columns, you can see there is another one, we call it the model, the data table has been changed. So okay, since we changed this one, maybe I can I undo the original data tables? I got this data. Now go back and look at the Cook's D. So maybe we can refit the models, calories and the distance. So now you can see there is an Cook's D here. So again, since we already have seen, we can see that this point is a high leverage point as well. Okay, because they have large X values and Cook's D is very high. It's more than 2. So if I ask you any questions, calculate the Cook's D, whether you see any problems or not, or calculate the studentized residuals, whether you have see any problems or not, you need to know how to calculate this one, how to say whether these values are usually a large values or not. So that's the summary of what we learned today, and we'll do some exercises in the next class based on this chapter, as well as we'll go over some other systematic errors. So we call it the violation of the normality assumption and the constant variance assumptions. Any questions so far? So far we just learned the idiosyncratic violation. We call it how to define whether an observation is an outlier or the leverage point, how to detect all these things. Okay, so we're just detecting the outliers, whether it is a high leverage point or high response values or unusual response values and so on. In the next class, we'll do some other part and hopefully we'll finish this and then we'll do some exercises. Any questions from you? Okay. Feel free to let me know if you have any concern, any questions for any part. I am always open to listen to you and I always want to accommodate according to whatever you are telling me. I hope everyone should do well in this course. Now another thing that for the exams or especially in exams, I put some critical thinking questions. Because first of all, if it is timed exam, I'll never put this on. Since it is a take-home exam, so you have more time to think about. So that's why the thing is, everything is from my materials. It's not outside from the materials, but you have to critically think little bit to answer some questions. And this is what I expect. This is my expectation. So I expect that you should learn the things and also think about critically to answer some questions. And if you don't have any question, then I can end the meeting. Otherwise, we can go over some questions, okay? Hope to see you in the next class, and I'll upload the materials and some practice problems for you.